I think we are going to move on to the next talk, which will be given by Dave Blewett. So take it away.
Sound check.
Yep, I hear you.
Okay, good. Yeah, I'm going to give a little review of why lunar swirls and magnetic anomalies are such great places to study processes related to regolith and dust. Next time step, please. So yeah, there are two persistent mysteries, the lunar swirls and the magnetic anomalies. So to start off with the swirls, I'm going to take kind of a historical overview here. The thing we know today as Rhino Gamma was seen in early telescopes, and it was thought to be a crater, and it was actually given the name Galileus back in the mid or late 1600s. Now the tail up to the north east doesn't look like a normal crater ray, and people realized that it doesn't cast a shadow, so it's not a highland ridge. Next slide. And you know, over the years, ground-based telescopic images improved and revealed it to be an albedo marking, which we now call Rhino Gamma. And I love these plates from the rectified lunar atlas, particularly the lower right low sun image from Mount Wilson. Look at that, 100 years ago. It was clear that Rhino Gamma is something funny. Next slide. Then came the space age, and we found out that there are swirls on the far side. Here's a Lunar Orbiter 2 image of the really great swirls in Mare Ingenii. Next slide. Yeah, so the swirls on the far side. We got to see this great view from Apollo 8 of a Goddard A crater and the really splendid swirls there all across Mare Marginis. Next. And in addition, we found out that there can be complicated sinuous swirls that are purely confined to the highlands, as you see the swirls near Firsov from Apollo 10. All right, next. Then, of course, the really big discovery from the Apollo era came from the subsatellite magnetometers. And they revealed that while the moon doesn't have a global dynamo field, there are areas of magnetized crustal rocks called magnetic anomalies, and that Rhino Gamma happens to correspond to one of these. And this is where we get into this question of why there's two persistent mysteries. Next slide. So one is, you know, what's the origin of the magnetized crust? And I'm not going to get into that here today. And then there's the completely separate question of what is the origin of the swirls, and as a corollary, how are they related to the magnetic anomalies? So let's look at those hypotheses for the origin of the swirls, I think, in the next slide. So the major categories that have been proposed are shown there. The first is the solar wind standoff. And the idea here is that the presence of the magnetic field attenuates the solar wind flux that reaches the surface in normal non-magnetic areas, and that this slows down the normal space weathering, soil darkening process that comes about through sputtering and implantation. And there are a set of ideas related to comets. The first was from Pete Schultz, and that idea is that gas and dust in the coma of a comet modifies the surface. And he has looked at that more closely in more recent years in his work with Megan Brooks Seal. And then there are the alternate sort of variants on that from Patrick Pinet and Larissa Starokina about nucleus fragments or meteoroid swarms that actually scour or plow the surface and expose fresh material. Then the most recent ideas have to do with unusual dust effects. And we have this concept from Ian Garrick Bethel where the interaction of the solar wind with a magnetic field sets up electric fields. And these influence the motions of electrostatically lofted dust, causing it to be attracted to or repelled from certain locations, and therefore accumulations of bright, fine dust particles. That's what the bright swirls are. And Carly Peters posited that, well, maybe these unusual skipping back and forth of these dust grains modifies the uppermost texture of the surface, perhaps destroying the so-called fairy castle structure that's present in normal areas, thereby modifying the photometric properties and giving you the bright swirl that we see. And Carly has also suggested that there could be some kind of magnetic sorting taking place based on essentially the maturity of these dust grains, their nanophase iron content, due to the actual magnetic field sorting things out. Next slide. Right, so all these hypotheses for swirl formation are related to regolith and dust processes, right? Space weathering, the relative roles of the micrometeoroids and solar wind. We'll hear more in the next talk from Jeff Gillis-Davis about that. Now, certainly, comet parts must strike the moon, whether it's more recently, as in the Schultz hypothesis, or certainly over lunar geologic history. Well, we certainly know that landing rocket exhaust can modify the photometric properties of the surface. Now, while deep accumulations of dust appear to be ruled out by the thermophysical thermal inertia measurements from Diviner, there could be thin accumulations of some kind. And, we know that there's evidence for low altitude motions, the Surveyor horizon glow, dust detector experiments, and so forth. Next slide. So I would say that the top questions related to dust and regolith at the magnetic anomalies are, the first one there is the opportunity to separate the micrometeoroid bombardment from solar wind exposure in space weathering. And then what does that tell us about space weathering on other airless bodies? Second, has the lunar surface been modified by the action of gas, dust, or other comet-related effects? And third, magnetic anomalies are predicted to have especially active dust environments. So can we observe such activity in situ? And what can these processes that are at work there tell us about what happens at other places on the moon or even on other airless bodies? So next slide. And so the answers to all those questions, we need to have measurements on the surface within magnetic anomaly. And a static lander mission is a great start, but really, in order to take full advantage of the science potential of these unique natural laboratories, a long-range rover is needed. And that's pretty much it. You could go to the next slide where I have just a celebrity portrait of Rhino Gamma. Thanks for listening.